Center for Integrated Nanotechnologies, or CINT. It's a Department of Energy Office of Science user facility, jointly operated by Sandia and Los Alamos National Laboratories. We are one of 5 nanoscale science research centers across the United States. The Department of Energy recently announced $179 million in funding for 3 microelectronics science research centers, or MSRCs. These are known as Meerkat, CHIME, and ILMIC. These centers are tackling some of the biggest challenges in microelectronics, from energy efficiency to resilience in extreme environments. Meerkat stands for Microelectronics Energy Efficiency Research Center for Advanced Technology. The project I'm involved in is the Nanoscale Research Center for Heterogeneous Integration Platforms. That's NSR CHIP. The focus is on revolutionizing energy-efficient microelectronics. As computing demand grows, driven by artificial intelligence, communications, advanced sensors, and autonomous systems, energy consumption is skyrocketing. So moderate improvements in computing efficiency can reduce the amount of energy infrastructure needed that we need to invest in power plants. So for example, a given AI query or token would take a lot less energy.
With the NSR chip project, what we're trying to do is put dissimilar materials on top of each other to improve their functionalities. And so where MBE, or molecular beam epitaxy, helps is because we're growing thin films, atomic layer by atomic layer, it helps us get crisp and defined interfaces between different materials and also get ultra-pure materials.
We're looking at integrating different kinds of materials, either monolithically or heterogeneously, onto a single device, and then we want to assess how these materials can work together. To do that, we want to have a way to rapidly characterize the material properties across different modalities, so that we can probe their applications not just at room temperature, but also perhaps in space, or their applications in quantum technologies as well.
So this is a flow cryostat, which is equipped to do deep level transient spectroscopy, which is a powerful technique to characterize defects in semiconductors. We can apply varying voltage pulses using a waveform generator to vary the filling and depletion of carriers in a depletion region in either a semiconductor or a junction of 2 dissimilar materials. And as we vary that temperature, we can observe the emission rates of these carriers with respect to interaction with defect states. And as these carriers interact with these defect states, we can actually see transients of the capacitance signal on a lock-in amplifier, which allows us to extract information such as defect energy and defect concentration. And this is my setup.
So the project I primarily work on is called Compact. Aim of this project is to make materials testing as easy and convenient and reproducible as possible. And what we are trying to do is create a wafer, or a platform as you will, and each dies contains many different microelectronics structures that are required for these testing of the materials. It will increase reproducibility because you can calibrate one material over another using the same structures without even changing them in every iteration. So that's the goal of this entire project, and we are mostly halfway through, and we are hoping to have results in a few months.
CHIME is a center for co-design and heterogeneous integration for microelectronics in extreme environments. CHIME is dedicated to research on microelectronics that can function in extreme environments such as very high temperatures, very low temperatures, and at elevated levels of radiation. There are 4 projects in CHIME. SEED aims to develop novel diamond-based electronics. SPICE is targeting cryogenic electronics and integrated single photon detectors. VIAS is looking at novel heterogeneous integration strategies for development of new detector systems. And NSOC is developing a new type of 3D monolithic integration based on solution-processed electronics and photonics.
My role within the NSOC project is to provide tools for the integration of soft, chemically synthesized nanomaterials with hard fabricated nanostructures. To achieve this, we leverage tools that exist at CINT, including dip pen nanolithography, and also this multi-probe system that allows us to deterministically place nanomaterials in surface features. The tool also allows us to characterize the properties of those materials in situ using up to 4 different modalities simultaneously. These modalities include those typically found in your average AFM system, but also extend to AFM Raman and NSOM. By achieving the co-location of these nanostructures, we're able to realize emergent functionality that differs from that of the individual building blocks.
So IMB Materials Laboratory is a multi-user research facility in Los Alamos National Laboratory. It is dedicated for conducting materials research with energetic ion beams. IBML has tandem ion accelerator and also implanters, which cover a very broad range of ion irradiation spectrum, including different ion species, energies, and flux. While there are a lot of different radiation environments in different applications, from fundamental level, the radiation damage effects are largely the same from a materials perspective. So we have ions coming in, or the charged particle, or neutrons or gammas coming in. They deposit energy into the materials matrix, which are made of electrons and atoms there. Depending on how they use the energy partitioning to the electrons or to the lattice atoms, the radiation damage impact is different. So in the ion beam laboratory, we can vary and tune the ion beam parameters to have a dominant effect, give energy to electrons, have a change of the electronic configurations through ionizations, excitations, or charge transfers. Or we can also transfer energy to the lattice atoms to displace them away from the original equilibrium sites, create point defects such as vacancies, interstitials, and extended defects such as voids and loops.
National Labs provide the unique suite of fabrication, characterization, and modeling tools needed for success in microelectronics research.
Together, we're building a foundation of transformative technologies that will impact society for decades to come. Finally, I invite you to come explore research capabilities in all of the MSRCs, Meerkat, CHIME, and ILMEC. Learn about the equipment and the people and the research that we're doing. Come share your ideas with us to advance microelectronic science and technology.